And let me remind you that last time we introduced the important notion of random variable and discussed some ways of defining the probability distribution of a random variable, and discussed some examples of it. Also, we introduced and discussed the important concept of expected value, which is a parameter that summarizes the information on the random variable, summarizes the probability distribution, and sometimes it's all we need to know about a random variable. Okay, this said, the next most important parameter is the parameter that characterizes the dispersion or spread. It's important to understand that with the same value of expected value, a random variable can be more dispersed or less dispersed. So the next thing after we have found out the expected value, the next thing that we will want to know probably is how dispersed the random variable is around the expected value. And this parameter that is the measure of dispersion is called variance. Variance. For a discrete, I hope you remember that last time we introduced this definition, discrete random variable. A discrete random variable is one whose values can be listed, can be presented as a finite or infinite list. And today we'll extend this concept to include continuous random variables. But okay, let me, at this point, give a definition of variance for a discrete random variable. The notation, well, this is or just capital V or VAR is typically used. And we take this sum over all the possible values of the random variable, and for each we form this difference, the value minus expectation squared times the respective probability. Okay? Now let's look at this and let's try to understand what it means. How is it a characteristic of spread? Now, mu, I think I mentioned it last time that mu is another way to denote the expected value. It's shorter, so we'll be preferring it in formulas. Mu is the expected value. And how is variance a characteristic of spread? Now, for each value that the random variable can take on, this is the deviation of this specific value from the mean, okay, from the expectation. And we square it and multiply by the respective probability and then sum up. So technically, we can speak of this as the weighted average of the squared deviations from the mean, okay, with probabilities used as weights. Now, this is the technical side of it. All right, look at this. Look at this square here. Is it really necessary to square these deviations? Maybe it would be simpler to just sum up the deviations multiplied by the probabilities. Well, the answer is no, and the reason is this. It's quite possible for the values of the random variable to deviate from the mean, well, upwards and downwards in such a way as to make the sum zero or close to zero, although the spread may be significant. Okay, do you understand this? We need to take these squares to not to lose any deviations. All right. This is the definition, but there is an alternative formula for this. which is often preferred in practical calculations. Okay, like this. Well, it's not a different definition, it's just a different formula equivalent to the first one. Well, we don't often discuss proofs, but just for a change, to give you a feel of how this can be done, let's discuss a proof of this one. All right, so this is going to be proof. And look at this. First step, we expand this square that appears here in this sum. Okay. Step 2, we expand the sum into 3 sums, and it's this. Okay, in this second sum, we can factor out -2 times m. We take it out and put this factor in front of the sum. And in the last sum, we take out mu squared. Okay? And let's look at what we get here. Now, what is this last sum? Do you notice that it's 1? Because it's the sum of the probabilities that correspond to all the possible values of the random variable. And the necessary condition for these probabilities is that they sum up to 1. And do you recognize this sum here? I really hope you recognize it, because it's the expected value that we introduced last time, which is mu. Okay? So this middle term here is -2 times mu squared, and the last one is just plus mu squared. So the total of these two, -2 mu squared plus mu squared, is just minus mu squared. Okay? Which is this. Let me not write it again. So the sum of the squares of the possible values multiplied by the respective probabilities minus mu squared. Okay? All right, and let's give it a simple example. Well, a certain young man, let's call him Joe. Joe has some beer in his fridge. Well, and the beer is in bottles. There is one 1.5 liter bottle and 2 liter bottles and 3.5 liter bottles and 4.33 liter bottles. Okay? Well, Joe has a considerable stock of beer in his fridge. All right. Now, at some point, Joe opens the fridge and, without looking, reaches his hand into the fridge and grabs a bottle at random. Now, because he does it at random, in this way, a random variable is created. If we look at the volume of the beer that he gets as a result. All right, what is this random variable? What is its probability distribution, and what is expected value and variance for this random variable? So let's denote it. Oh, okay, X, the conventional name for the random variable in theory, and this is the volume of the bottle that he gets as a result. Okay. Now, what is the probability distribution? First, the possible values are these: 1.5 to, I'm sorry, correction, this is a 1 liter bottle. So 1.5, 0.33. All right. So the possible values are 1.5, 1.5, 0.33. And the corresponding probabilities are, how do we compute, how do we get the probabilities? How many bottles are there in total? It's 1 here, 2 plus 3 plus 4, which makes 10. Okay. The probability, if the choice is made at random, then the probability of extracting one particular bottle is 1/10. Okay, and because there is only one bottle of this volume here, this probability is 1/10, and for this it's 2/10 or 1/5. For this it's 3/10, and for the fourth choice it's 4/10 or 2/5. Okay. All right, this is a probability distribution. And what is the expected value? Again, let me mention this again. Mu is a synonym of E. All right, we multiply 1.5 by 1/10, and then we had 1 multiplied by 2/10. Okay, now we multiply the possible values that this random variable can take on by the respective probabilities and sum up. This is the definition of expected value. And this is what we get as a result. Now, the expected volume of the bottle that Joe can get in this way is 0.632. I mentioned it last time, but it's a good idea to say this again. Now, this is not a volume. This is not the volume of any of the bottles that he has in his fridge. There is no such bottle, okay? And you should not expect that the expected value must be equal to one of the possible values. No, it's not necessary, and in this random variable, it's not so. Okay, but this is expected value, which is something that we did last time. Now, the new thing today is variance, and let's compute this. We have an alternative here. We can use the basic formula, the definition, or this other formula that is more typical for hand computation. All right, let's use formula number 2. Then the variance is going to be 1.5 squared 1/10 plus 1 squared 2/10 plus 0.5 squared 3/10. Okay, this is the sum of the squared values multiplied by the respective probabilities, and we need to subtract mu squared minus this squared, and the numerical answer here is this. Okay, now simple enough. Now, actually, variance, although it's an important theoretical instrument, is not a very convenient measure of spread in practical terms. And there is a reason for it not being a convenient measure. Let's discuss this question. Look at this. X is a physical variable. It's measured in certain units. Now, these figures are given in liters. And because they're given in liters, X is in liters. And look at this. In the expression, in the formula for the expected value, the separate values that the variable can take on are multiplied by probabilities. Probabilities are dimensionless. It's an important thing to understand. Probabilities are just numbers. They are not measured in any physical units. So in the formula for expected value, liters are multiplied by numbers. And the result is also in liters. Okay? Well, and what do you think of this? What is the unit of measurement that should be used for this, for the variance? Look at the formula. On the right-hand side here, liters squared are multiplied by probabilities. And probabilities are dimensionless. So the result is in liters squared. This is the great difficulty in using variance. It has a different unit, okay? Because it has a different unit from the variable itself, it's difficult to interpret the numerical answer, the numerical value, in any reasonable way, okay? For that reason, another measure of spread is introduced, which is the square root of this, the square root of variance, and it's called standard deviation. Standard deviation. Okay. Well, this is the accepted notation for it. It's the lowercase Greek letter sigma. Okay, and by definition, it's just the square root of variance. Well, this subscript x is quite often omitted if it's clear from the context what random variable sigma refers to. Okay. All right, let's use an example to illustrate how sigma is a better measure of spread than variance. Okay, suppose you conduct a field marketing survey aimed at finding out the distribution of retail prices for a certain make of mobile phone. Okay, different retail outlets set their own prices and they vary. There is not just one single price. So retail prices for a mobile phone. Well, because they vary, you can describe this situation in terms of random variable. You can say this: if we choose one retail outlet at random and inquire about the price, we get a certain value, specific value of something that is actually a random variable. Okay, so by making this random choice and finding out the price for this particular item, we create a random variable. All right. Now, suppose your finding in this marketing survey is that mu is $250. Okay, and variance is 64, and I am not really sure how I should write dollars squared. Is it this? Should I use this symbol or not? I must admit I've never encountered this symbol squared. So let me write it in letters, in full. Dollars squared, like this. Okay. So, what can we make of it? Is it a large spread or a small spread? It's actually impossible to make any conclusions because these two quantities are measured in different units. This is in dollars and this is in dollars squared, and there is no way we can compare one and the other. Okay? What's more, if you choose a different unit, for example, if you switch from dollars to rubles, what happens to these two? So suppose you now express this random variable in dollars. Well, I'm sorry, it was in dollars, now it's in rubles. I'm not sure about the exact exchange rate, but it's something like 35 rubles per dollar, I guess. Let it be just exactly 35. Then if you express these prices in rubles now, what happens to this and to this? Now, because each particular price is now measured in rubles, which is a smaller unit, the prices are multiplied by a factor of 35, okay? And accordingly, this will be multiplied by a factor of 35. So mu now, let's call it, well, by the way, so far as I know, they have finally decided on the notation for ruble, or on this international notation for ruble, and it's this. Well, I'm not sure it's a good graphical representation of it. Well, is it correct? Has it been established? Because I know that there was this long discussion about what is the best way to show ruble, but I think this is the final version. So, expressed in rubles, the expected value now is 35 times 250, and it's going to be 8,750. Okay, but what about variance? Variance, well, shall we multiply it by 35? Or maybe by something else? Because we now use a smaller unit of measurement, all the prices are multiplied by a factor of 35. And the expected value is multiplied by 35. But because variance uses squares of these prices rather than just these prices, the variance will automatically will be automatically multiplied by 35 squared. Okay, so now it's 35 squared multiplied by 64, which is this. Now, I think you now appreciate that it's really difficult to work with variance as a practical measure of spread. Now, in these units, 64 is something like one fourth of mu. Variance is 1/4 of mu. But in other units, variance is actually greater than mu. What can we make of it? Well, nothing actually. But let's see what we get if we switch to sigma. Now, sigma here is 8. And 8, if you compare it with mu, is, well, very approximately 1/30, okay, of mu here. And sigma expressed in rubles is the square root of this. It's just 35 times 8, and this to 280, which I want to emphasize this. Sigma in this new currency makes the same proportion of mu, of the value of mu in the same currency. So the proportion of these two is just the same as the proportion of these two. So it's a very important property of sigma. It doesn't depend on the unit of measurement. I mean to say the proportion of sigma and mu doesn't depend on the unit of measurement. All right. Now let's take some simple but important examples. Our favorite random variable that arises in a Bernoulli trial. Okay? The probability distribution, let me remind you, is this. Two possible values, and the respective probabilities are p, just p, and q, which is equal to 1 minus p. All right. Now, I think last time we computed the expected value of this, but let's do this again, and then we'll go on to compute the variance and sigma. So, mu is equal to 1 times p plus 0 times 1 minus p, which is just p. So the expected value of a Bernoulli, of the random variable that arises in the Bernoulli trial is this. Now what about variance? Okay, it's 1 squared times p plus 0 squared times 1 minus p minus p squared. Well, this is formula number 2, but we would arrive at the same thing if we used formula number 1. All right, this middle term is 0, so what it boils down to is p minus p squared, or p times 1 minus p. Or else it's p times q if we use this other notation, if we use q. All right. Now let's comment on this. First, let's plot a simple graph. Because p is a probability, it can only take values between 0 and 1. Okay? Look at this expression, p times 1 minus p. What kind of function is that? I'd like you to notice that it's a quadratic function, okay? And the graph is a parabola, and because the coefficient of the quadratic term of p squared is negative here, it's a parabola that opens downwards. And also, if p is 0, it's 0, and if p is 1, it's also 0. So it's like this. And what's the highest point? Well, the highest point is attained at p equal to 1/2. Okay, and the value of p times 1 minus p at this point is this. Okay. Well, let's look at the endpoints here. Do you understand the implication of variance being 0 at the endpoints? Well, variance is a measure of spread. 0 variance means no spread. No spread means that this variable is no longer a random one. Okay? Because to be a random variable, it must have some spread. Well, and actually it stands to reason, because if p is 0, okay, actually it's a Bernoulli experiment where success cannot occur. Only failure is possible. It's no longer a random variable. And the same thing can be said here. Success has probability 1, and failure is just impossible. So at the endpoints, the variance is 0, which corresponds to the fact that it's no longer a random variable. Okay, and we just agreed that variance is not a good measure of spread in practical terms. Let's look at sigma here. Sigma equals square root of p times q. And the graph is rather similar to this one. It's again 0 here, and it's again 0 at 1, and the highest point now is 0.5, like this. And it's something like this. I'm not sure it's a perfect graph, but okay, this is the best I can do. All right, this is the Bernoulli trial for us. Okay, and this is an important particular case. If P is 1/2, which can be illustrated by the experiment of tossing a fair coin, equal probabilities. Then variance has value 0.25, and sigma has value 0.5. All right, series of n Bernoulli trials. Well, I'm not writing this, but we always assume that these Bernoulli trials are independent and have the same probability of success. Sigma is going to be square root of n times p times q. Okay? Well, this follows from the binomial distribution. But there is something here that has a greater significance and a wider application than just the binomial distribution. Look at this. N Bernoulli trials means n independent, identically distributed random experiments, such that in each sigma is square root of p times q. Okay? Now, please pay attention to this n here. This n is under the square root, which means that as n increases, sigma increases not proportional to n, but proportional to the square root of n. Well, actually, it's a very, very important fact, and it has general meaning and general significance in probability theory. All right, and this particular random variable, it is a direct consequence of the binomial distribution. All right, we'll talk about this later. We'll try to suggest some justification for that. At this point, just try to pay attention to it and memorize it. All right, for Poisson distribution with mean lambda. Well, obviously, mu, which is the mean, is just this. What is very characteristic of a Poisson distribution is that the variance is just the same number. The variance is equal to the mean, and sigma is equal to the square root of lambda. Actually, this identity here is often used to check whether the Poisson distribution is an appropriate probabilistic model to describe a certain process that you want to study. Okay? Well, suppose you want to develop a probabilistic model, and your guess is that Poisson distribution is an appropriate choice for your particular situation. This is one of the ways you can at least make a first step in this work. Look at these two values. You can, if you have some extensive data, you can compute approximations, experimental approximations to these two, and comparing them, you can see whether they are very different or not. If they are really different, Poisson distribution is not a good idea. It's just a wrong choice. Okay. Well, if you don't have any questions here, let's move on and discuss a very important theoretical statement in probability theory, which is Chebyshev's inequality. As I told you at our first lecture, Chebyshev was a Russian mathematician of the 19th century who made a very, very significant contribution to the modern probability theory. And one of the things that he did is this. Suppose x is a random variable with expected value mu and standard deviation sigma. What's important, we are not assuming any law, any probabilistic law for this. We don't assume that it's binomial or Poisson on anything else. Okay? It's just any law. We only assume that we know mu and sigma. Well, one of the ways to write this inequality is this. Okay. Well, look at this. Let's try to understand what's written here. Maybe this illustration will help. Now, this point is mu, the expected value. Now, look at this inequality. It means that the distance between x and mu is greater than or equal to the product k times sigma. Okay. Another way to say the same thing is, let's plot mu minus k times sigma and mu plus k times sigma. Okay, now the points that satisfy this inequality lie either here or here. Okay? So, in simple words, we are talking about this occurrence, this event, that the value of x is distanced from mu by more than k times sigma. Okay, and now according to this inequality, the combined probability, the total probability of this event and that event is less than 1 over k squared. Well, imagine now that we give k larger and larger values, which means that we consider a wider and wider interval, and these tails are farther and farther away from mu. Then the right-hand side here will approach 0. Okay? Do you understand the implication of it? If sigma is a positive value and a finite value, if it's known, then with a larger and larger probability, all the values of x must get into this interval if k is increased. Okay? Well, I don't expect you to be happy with this right away. Okay, maybe it'll sink in and become familiar. But let me tell you, this inequality is of fundamental importance. One of the things that depends on it is the so-called law of large numbers that we are going to mention a bit later. Okay, now let's give this an example, just an example. Let's select this. So we just give k a specific number, it's 2. Then p, probability that x minus mu exceeds 2 times sigma is less than or equal to 1 over 2 squared, which is this. Okay? This can be rewritten in the way, the probability that mu minus 2 sigma plus 2 sigma is greater than or equal to like this. So now well, it's just a different way to say the same thing. If this is mu minus 2 sigma, mu plus 2 sigma, the probability that the value of x gets within this interval is at least equal to 0.75. Okay? And again, let me again say this. We don't assume any specific law, any probability distribution for this random variable. We only assume the existence of mu and sigma. Now, for a specific law, for a particular probability law, typically, actually this value on the right-hand side is larger than that. Now, the Chebyshev inequality guarantees that for any law, this probability is at least equal to 0.75 for k equal to 2. But for a particular law, it can be a larger value. Let's say that for so-called normal distribution, which we are going to discuss very, very shortly, and this is probably the most important distribution, this value is equal to 0.954. Okay? So for any random variable with any mu and any sigma, this must be true. For a particular random variable, it can be and typically is a larger value. For example, for the normal distribution, in this, well, this probability is just equal to 0.9954. All right. Well, if you have no questions here, let's move on. And the next item for us will be continuous random variables. So far, all the examples of random variables that we discussed belong to this to one of the major categories. Well, it was our first category of random variables. It was called discrete. It's called discrete random variables. And although I've said it more than once already, let me say that again. A discrete random variable is one whose values can be arranged as a list, either finite or infinite. Now, not all random variables are like that. Sometimes there is no way we can list all the values that can be taken on by the random variable. For example, suppose we perform a field study of the distribution of body weight in a certain population. Okay? Well, body weight is, if we measure it very, very accurately, okay, it remains to be defined what it means, what very accurately means. But theoretically, a body weight is a quantity, a variable that varies in a continuous way. It can take on, again, in theory, any real value. And real numbers are not something that you can arrange as a list. Okay? They form a different kind of set. It's called continuum. It's a different story. Let me not go into this because it's kind of tough. But just for us, for the purposes of this discussion, there are infinite sets that can be listed. They're called countable. And there are infinite sets whose members can't be listed. And the main example of this is the set of real numbers, or the set of real numbers contained in some interval, finite or infinite. Okay? Well, another example like this. Suppose we look at the exact amount of liquid put in a bottle by a machine. Again, it can be any real value within certain limits, of course. Or maybe the exact amount of time spent by a doctor to receive a patient, to treat a patient. Anything. Well, you can come up with a lot of examples of your own of this kind. Okay, now how is a continuous random? Let's write it down just to be formal. A definition. A random variable is called continuous if its values fill an interval. Okay. By this I mean, well, it can be an infinite interval. It can be the entire real line from negative infinity to positive infinity, or it can be some bounded interval. Well, bounded or not. Okay. So the entire real line is also a particular case of this. A semi-infinite interval is also part of this, and just an interval from A to B is also a possibility here. All right. So looking at this, how is a continuous random variable different from a discrete random variable? Why do we have to invent a new name for it and treat this as a separate category? Now, the new thing, the difficult thing here is this. The way to describe or define a discrete random variable is by presenting this table, the table of possible values and the corresponding probabilities. Now, this is impossible for a continuous random variable. Exactly this is impossible. And the reason is that the values of a continuous random variable just can't be listed. You can't list all the real numbers in an interval, or all the real numbers on the entire real line. They can't be listed. Let's write it here. Values, okay, just as a reminder, values over continuous random variable can't be listed. Okay? And this is how it's different from a discrete random variable. But, okay, the values can't be listed. Then how are we supposed to introduce the probability distribution? Okay? We need a totally separate, a totally different approach to this. What's more, there is a very serious issue here. I'll try to approach this difficulty by first drawing an analogy. Okay? Suppose this is an interval, a segment, a line segment, a segment on a line, okay? Interval from A to B. And it has, the segment has a length. So the length is B minus A. If B is greater than A, then B minus A is a positive number. It's an interval of positive length. This is okay. But the next question, well, actually it's quite difficult, but we're quite accustomed to it, so we don't perceive it as difficult. The question is this: and what's the length of a point on this interval? Let's pick just one point. What length do we associate with a point? And actually, it's a difficult question, because a point doesn't have a length. The length is 0. The length of any point, we associate positive length with a segment, not with a point. So any point on this interval has 0 length, and at the same time, the interval that consists of these points has a positive length. If you think of it, it's a bit of a paradox, or maybe a lot of a paradox, okay? It's a very deep question in mathematics and in geometry. So we think of a segment as consisting of points. Each point has 0 length, and nevertheless, the entire segment has positive length. So how does it work? How do these 0 lengths sum up to produce a positive length? Now, again, this is a difficult question and a serious question in mathematics and in mathematical physics and the rest of it, but we're just accustomed to it, and we don't really see it as a big difficulty. But here we again meet with the same difficulty. We have a continuous random variable, and let's ask ourselves, what probability do we ascribe to one point, to one specific value? Because it's a continuous random variable now, the only possible number is 0. We cannot ascribe any positive value to one point in an interval, or to one real value among a continuous set of real values. So each specific value in a continuous random variable has probability 0, okay? I'm underlining this because it's a difficult thing to understand. So each specific value has probability 0. Then how do we define the probability distribution if the probability of which possible value is just 0? We need a different approach to this. And this other approach is based on the concept of cumulative probability function. Actually, we mentioned it last time, but in application to discrete random variables, cumulative probability function doesn't offer any real advantages. Its real advantage is that this tool for describing a random variable actually links discrete random variable and continuous random variable. It's the general way to introduce any random variable. Let me write again the definition. So cumulative probability distribution well, sometimes I lose track. Cumulative. Let's keep to the standard terminology and standard notation. Distribution function. Okay, and accepted. There is this accepted abbreviation. Now the definition is this. First, the standard notation for it is F capital, and for any particular value, little x, F capital cumulative distribution function is defined to be the probability that the random variable takes on a value less than or equal to little x. Okay. Well, again, we can define and we can study the cumulative probability function for any random variable. This is the most general way to describe a random variable. Okay, now let's try to say something about this function. Do we know anything about it already? Well, we do, because the right-hand side is a probability of some kind. This function f capital must be non-negative. Okay, so property number 1, f capital is always non-negative. Okay? Next. What about this? If x goes to negative infinity, what do you think? I think it's better to first ask you this. Look closely at this definition. The probability, the right-hand side, is the probability that the random variable takes on a value to the left of this given little x. Now, suppose we move this little x to the right indefinitely. Suppose x here, little x, goes to positive infinity. What do you think? What happens to this probability? Yes? No. I thought you had a theory. Well, let me ask you first. If x increases, x lowercase increases, what happens to this quantity? Does it increase or decrease? If this x goes to the right, does the probability that the random variable takes on a value to the left of it, is it going to be larger or smaller? Well, Well, of the two options, you chose the wrong one. It's going to be larger, okay? If x lowercase goes to the right, the probability by this definition, by the meaning of what's written here, it can only increase. Well, if x lowercase here goes to positive infinity, then there is a limit to this increase, okay? The probability can't be greater than 1. And if x lowercase here goes to positive infinity, this probability approaches 1. So the limit as x approaches positive infinity is 1. And if we do it the other way, if x lowercase goes to negative infinity, the limit is 0. So the limit is 0 at negative infinity, and it's 1 at positive infinity. And what's more, I don't know where I should write it. Let me write it here. F capital of little x is well, not necessarily increasing in the strong sense, but it must be non-decreasing. Non-decreasing. All right. Something like this. Something like this. So this is x, and this is f capital. 0 limit at negative infinity, limit of 1 at positive infinity, increasing positive. These are the properties of any cumulative distribution function, regardless of the law, of the probability law. Okay, this is one of the ways to represent a continuous random variable, but we can do something else here. Look at this. If we identify 2 points on the real line, then the increment of the two values of f capital gives the probability that x capital, the random variable, gets within this interval. Okay? So it follows directly from the definition of the random variable. Let's write it here. Probability that okay. Well, suppose now we fix the length of this interval and move it along the real line. Well, I'd like you to notice that the probability that corresponds to this interval will depend on the location, on its location on the line. So here, this is comparatively small, and And this is much larger, although this length is the same as that length. So we associate positive probabilities with intervals here. This is point 1. And point 2 is this. For a given length of the interval, the probability depends on the location of the interval on the real line. And this second aspect we would like to study and give a formal expression of. And the formal way to express it is this. We introduce, apart from cumulative distribution function, we introduce this. The derivative of f capital, this prime here, stands for derivative. The derivative of f capital with respect to x lowercase. Now, look at this. The derivative can be explained. Another way to talk of derivative is talk in terms of slope or gradient of the function. So the derivative is the largest here because this area is the area of the largest slope. And the derivative approaches 0 when we go to positive infinity, and again it approaches 0 when we go to negative infinity. Okay? So typically, the typical picture would be this, something like this. Okay? I think what's presented here roughly, very roughly, corresponds to this cumulative distribution function. There is a certain maximum that corresponds to this area here, maximum slope, and at the extremes, this derivative approaches 0. Okay. Now we should probably have mentioned that at once that because the cumulative distribution function is non-decreasing, this derivative is greater than or equal to 0. It's non-negative. Okay. Well, okay, and also the integral from negative infinity to positive infinity of this is, well, I don't know if it makes sense to ask you what this integral is. Okay, let's not waste time. It's 1. Okay, it's the difference between the two extreme values of the cumulative distribution function, which is 1. Now these are the main properties of this other function, and it's called probability density function. Okay, density like this, and PDF is the standard abbreviation for this. Now, maybe, well, sometimes or maybe often, trying to explain this, the authors of textbooks use this analogy from mechanics. Okay, think of a body that has a volume and a mass. Now, the mass of any given point in the body is 0, okay, and still the entire body has a finite mass. Now, this is a similar situation. The probability associated with any given point is 0, and still all these points put together, that is the set of possible values, has a finite probability that is actually equal to 1. Okay, but in this mechanical situation, we can also talk of density. So the mass associated with any point is 0, but we can choose a small volume, look at the mass, and divide the mass by the volume. In this way, we get what we get is density. And the word density here comes from this analogy, okay? So we can't associate positive probabilities with points, but we can associate a certain value of this density function with a point. Now we are going to define what expected value means for a continuous random variable and what variance means. Expected value. View. Well, expected value and variance are introduced through this function, probability density function. Okay. Well, look at this. And if you compare it with the definition of expected value for a discrete random variable, you'll notice that what was a sum is now an integral. The value, the possible values are still there, okay? But in the sum that gives the expected value for a discrete random variable, in this position we have probabilities corresponding to the separate values that are possible for the random variable. Here, x is a possible value, but now it's a value from a continuous set, and we multiply it by the density function, okay? And then we take this integral. Okay, this is expectation. Actually, it's a complete this is completely analogous to the definition of expectation for a discrete random variable. All right, and variance, again, it's perfectly analogous. It's the integral from negative infinity to positive infinity. And again, we take this difference. It must be familiar by now. This is the deviation of the value x from the mean, and we square it, and then we multiply it by the density function and integrate. Okay, these are the definitions. All right, it's time to give some examples of continuous random variables. Now, the simplest and quite important example of a random variable is the uniform. Okay. Well, maybe before I go on with this example, maybe I still need to say a few words about this. Now, if you look at this function, how would you explain that it has a larger value here than, say, here? What's the implication of it? What does it mean in simple terms, in words? I don't mean this technical definition, this derivative thing. But in simple terms, it means that if you take a small interval and select it here and compare it with the interval that is selected here, the probability associated with an interval in this area will be larger than the probability of the same associated with the same length chosen somewhere else. Okay, so this function gives us an understanding, an idea of comparative likelihood of the random variable getting into different areas. But we have to always keep in mind that we are talking about probabilities associated with intervals and not with points, with separate points. Okay? And this said, the probability density function gives us characterizes the comparative likelihood of the random variable getting in different intervals. All right. Now, uniform random variable. Let's discuss this situation. It's, by the way, quite practical, and everyone knows this from his or her own experience. Now, I don't know whether, by the way, I don't know whether my students are regular users of the underground. Maybe you always drive a car, like a Porsche or something, I don't know. Myself, well, as far as I'm concerned, I'm a regular user of the underground. In the underground, there are these regular intervals between the trains. Okay, so suppose suppose, just for the sake of this discussion, that trains run every 3 minutes. The trains run every minutes. Well, suppose I arrive at the platform at some random point in time. Okay, then what is the time that I'll have to wait for the nearest train, for the next train? Okay, well, obviously this length of time can be anything between 0 and 3 minutes. It can be more, it can be less. Okay, so we know that. So if we use this capital T for the well. Before saying this, we need to understand and state that T, which is the time that I'll have to wait for the next train, is a random variable. If I arrive at a random point in time, there is no way of telling in advance how long I will have to wait. Is it 1 minute or 2 minutes and any other time? All right. So this is waiting time for the next train, and it's a random variable. And the next thing to mention is that it's a good example of a continuous random variable. Okay, do you understand this? Waiting time can be any real number between 0 and 3. It's not some finite list of values that can be arranged as a list. All right, and the next question is this. Looking at this probability density function that characterizes comparative likelihood of different areas in the distribution, different regions. Let me ask you this. If I arrive at the platform at a perfectly random point in time, is it more likely that I'll wait something like 1 minute or something like 2 minutes? Is 1 minute of waiting time any more likely or any less likely than waiting 2 minutes? Well, intuitively, there is no difference. If it's a random point in time, there is no, I don't know in advance whether the point will appear the next second or after 1 minute or after 2 minutes. And there is no reasons to expect that waiting for 1 minute is any more likely or less likely than waiting for 2 minutes. Which means that instead of this kind of curve, we have a horizontal line. Okay, the probability density function must be horizontal here. It's like this. Like this. Do you understand what I'm trying to say? And this idea is reflected here in this title, uniform. There are no more likely or less likely regions here. Okay, all the intervals are equally likely. Okay, let me tell you. Well, let me ask you as a check. What's the height here? What's this value? Okay, thank you a lot, Mr. Makarov. You saved my day. You're my hero, because I was about to think that nobody would give me any answer, because the integral under this curve must be 1, okay, and because this whole interval, where it's defined as 3, so this is 1/3, okay. And by the way, it's going to It's going to be on the tape. So you did it for the whole world. You showed that you actually know something. All right. I feel much better. Okay, this is 1/3. So this is an example. By the way, it's quite a realistic example of the so-called uniform random variable. General uniform random variable. Well, it's defined in this way. Well, this is, in this example, the interval on which this random variable is only defined is from 0 to 3. In the general case, it can be any interval from A to B, and the probability density function is 0 if x is less than A, then it's 1 over B minus A if x is between A and B, and then it's 0 again if x is greater than B. Okay, so the probability density function like this, 1 over B minus A, it's equal to 1 over B minus A everywhere over this interval, and it's 0 everywhere else. Okay. Well, the cumulative distribution function is 0 if x is to the left of A, and it's x minus A times B minus A if A is this. You can easily check that if x is A, then this is 0, and if x is B, this is equal to 1. And it's 1. It's 1 if x is greater than B. So the probability density function, let me try to represent it here. It's 0 to the left of A. Then it increases in a linear manner like this to and reaches 1 at the right end point, and then it's 1. Well, because probability density function is constant and cumulative distribution function is the integral of PDF, then cumulative function must be a linear one, and it is. And something else here. Now, suppose you okay, so E of x. Well, looking at this, you can easily guess what the expected value is. It's uniform. It's distributed in the uniform way over the interval from A to B, and the expected value is just the middle of this interval, B plus A minus over 2, and the variance. Well, this is not so intuitive, B minus A squared over 12, but it's a good example, by the way, for you to do independently. Please try obtaining this formula at home. All right. Apart from being having some importance in its own right, the uniform distribution plays an important role in modeling some other distributions. Okay, and this is what I want to say. Suppose you develop a probabilistic model, and in this probabilistic model you need to obtain a series of values distributed according to some law that you suggest, you introduce. If it's some known law, such as a binomial distribution or Poisson or normal distribution, which we are going to discuss a bit later, then the so-called random number generators for these known types are available Well, for example, in Excel, okay, Excel on your personal computer, you have Excel, and Excel contains a random number generator for the normal distribution and for the binomial distribution and for the uniform distribution. But suppose you invented a random variable, a law, a probability law of your own, okay, that you want to introduce a new distribution that suits the needs of your particular model. How do you get a series of values distributed according to this new law? This is, well, the uniform distribution can help in this. And this is how it works. Now, let's use this U capital for the standard uniform distribution. And the standard uniform distribution is a uniform distribution on the interval from 0 to 1. Okay? And that's it. This is the only characteristic of it. Okay, now let's say that x is a random variable that has the cumulative distribution function f. Well, this is what you introduce. You introduce a new random variable and you write a cumulative distribution function for it. Okay? And then x is equal to f capital, the inverse. Do you remember this term and this concept, the inverse function? So -1 here stands for inverse function. Okay. Then x is the inverse function of u. What does it mean in practice? On every computer, you have a generator of random numbers distributed according to this standard uniform law. And if you just write f capital and the inverse for it, then generating a stream of numbers, a sequence of numbers distributed according u, and applying the inverse of f to these numbers, what you get as a result is a series of numbers distributed according to your to the distribution that you just invented. Okay, it's a powerful and convenient thing. For example, well, I still have a couple of minutes. Let me just start this example. Suppose f capital is 1 over p okay, 1 divided by p times arctangent of x plus 1/2. Now, do you understand what the probability density function for it is? Again, here we need to recall something from calculus. It's this. Okay. So you have a guess that maybe this probability distribution function will work well in the application that you are developing. Then you need a way to generate a sequence, a series of numbers that follow this distribution law. Okay, and this is how it works. You use a random number generator for the standard uniform function, and then x equals tangent pi over u minus 1/2. Okay, and this is what you do. This is quite technological, very easy to realize, and you can do it on your own personal computer tonight. Okay, I think my time is up. Thank you. See you next time.